I'll be talking about adversarial risk analysis, which can be viewed as a Bayesian version of game theory. My publisher told me that I ought to show the cover of the book that is coming out in July and shamelessly flog it wherever I go, so that's what it will look like. Adversarial risk analysis is an attempt to solve, to combine two different areas. Classical game theory makes unreasonable assumptions about what people know about their opponents. It assumes common knowledge, it assumes perfect rationality, and often it makes other assumptions as well. And behavioral economists have shown very clearly that that's just not the way human beings think. When human beings approach some sort of game, some strategic question, they don't think the way John von Neumann does. They think differently. And so we would like to try and come up with some realistic way of describing human thinking and reasoning about adversarial problems. In parallel, there is probabilistic risk analysis, which is basically the statistical approach to handling a non-strategic opponent. You put a distribution over the actions of nature and then make a choice that maximizes your expected utility against that distribution. And clearly that's not a strategic calculation, although at least in the United States, many of the people in the Department of Homeland Security and other decision makers seem to think that doing some sort of probabilistic risk analysis is their way in to handling security problems. Neither one seems adequate to the real questions that we observe in the world, and this type of situation arises in lots of places. You've got corporate competition, you've got federal regulation, where there are typically three parties to the game: the government, the industry, and people in general. And you also have sort of counterterrorism type things. So I'm going to talk about a Bayesian version of game theory, which is not the Bayes-Nash equilibrium, but something a little bit different, in which you build a decision theoretic model for how your opponent reasons and then maximizes your expected utility with respect to that. The old decision analyst people were Jay Cadane, Pat Larkey, Harold Rifa, and they had these ideas out there, but Harsanyi hates them. Roger Myerson has a Nobel Prize, and so you have to respect that. But he also is totally against the decision analytic approach to this kind of problem. And his argument is that there's a fundamental difficulty that will make the decision analytic approach impossible to implement. In order to assess one's subjective probability over the distribution of other players, player I would have to figure out what they would think would be his rational position. And since that's the problem he started with, he's stuck. And so Myerson says, this difficulty would force player I to abandon the decision analytic approach entirely and instead undertake a game theoretic approach in which he tries to solve all the people's decisions simultaneously. But of course, we have massive evidence that that's not what people do. So I think he's a little quick to throw out decision analysis in this context. So instead of getting rid of that strategy, we're going to try and come up with a smarter way to operationalize it. And there are different ways to do that. One version is sort of a version of level K thinking, which I'll be talking about later on. We'll also talk about Bayes-Nash equilibria, mirror equilibria, and other types of rationality. So the adversarial risk analysis framework is nice, I think, because it conveniently partitions your uncertainty about the decision-making problem into three pieces. The first part is aleatory uncertainty, and that says if I decide to do this and Qiming decides to do that, then the outcome from our joint decision may still be uncertain. So we condition on our choices and then look at what the outcome is going to be, how much money you will make or how much money I will lose. That would be the type of thing that could be random, but it doesn't involve strategy because we've conditioned on the decisions that we each make. So that part can be handled by straightforward statistical risk analysis. And at this point, I should probably add a small footnote. I am keenly aware of all the difficulties that arise when doing statistical risk analysis. Expert elicitation is a problem. People have all sorts of biases. There are issues in trying to do statistical risk analysis. But nonetheless, it's a well-understood field. People apply it all the time. And so in some sense, that portion of it is a solved problem. A second type of uncertainty is epistemic uncertainty. And epistemic uncertainty arises because I may not know what K-means utility function is. I may not know whether K-means is an optimist or a pessimist. I don't know what resources K-means might have. And as a Bayesian, I can put subjective distributions over all those unknown quantities, and that will represent my full uncertainty about K-means attitudes, beliefs, capabilities, probabilities, all of that stuff. The last one is the most difficult. That is concept uncertainty. And that it refers to the solution concept that, say, K-means is using in analyzing the problem. It could be that K-means is an old school Nash equilibrium seeking guy. Okay, if he is, then I know how he's going to frame the problem and what sort of tools he's going to use to solve it. It could be, however, that he is a level 3 thinker. So he thinks, I think that you think that I think that you think, and then he stops. It could be that he does a mirror equilibrium. He could do other things as well. So I don't know what kind of reasoning he's going to use in trying to frame the problem. And that is where most of the strategic uncertainty comes from. So adversarial risk analysis allows us to handle those three different things separately, and that turns out to be very convenient. Let me talk about this in general, and the second part of this lecture is going to focus on auctions, and many of the ideas will become much more concrete when we come to the auction theory examples. But for right now, I'm going to be sort of general, and we'll apply it to two things, but the real illustration of the range of this method, I think, will come in the second talk. All right. What I'm going to do is try and build a model for the decision-making process of my opponent. And adversarial risk analysis does not try and solve the problem jointly for all participants at once. Instead, there's one agent whom you are supporting, and you're performing the analysis from his or her point of view, and you want to use their information. So the supported agent is going to have a subjective probability about the actions of each of the opponents. So there'll be a certain probability that K-Ming is going to try and smuggle a bomb onto a plane, and I have some probability over him doing that. There are going to be subjective conditional probabilities about the outcomes of all of these things. If he smuggles a bomb onto the plane, will he be successful in detonating it? How many people will die? How much will it cost? So those would be the probabilities conditional on all the possible actions. And finally, I have to know what my own utility function is. I have to know how much I value different outcomes. And we imagine that Daphne believes a problem has probability P sub D of A of choosing action A. And that's the hard one. Trying to figure out what a rational person would believe is the probability of your opponent chooses a specific action is the hardest thing to get a hold of. And we'll talk about how to do that in a moment. But suppose we have some machine that allows us to generate a distribution over the action space of my opponent. That's really helpful. I also need to have the probability of all outcomes conditional on my choice D and my opponent's choice A. And I also need to know my utility function, which is the utility of choice D, choice A, and outcome S, where S is the uncertain outcome that's random. If you'll allow me that notation, then my optimal choice should be D star, which is going to be the thing that maximizes the expected utility under my uncertainty about all of the things that are going on here. So as a Bayesian, I have these beliefs, and if I can formulate those beliefs in a mathematical way, then I would always want to maximize my expected utility, and this is how I would do it. And getting there is the tricky part. As I've said, the most difficult quantity to obtain is pi sub D of A. The others, one uses traditional risk analysis, and the other simply assumes that you know what your personal utility is. And most people are actually don't have much trouble expressing, or at least ordering their utilities over the outcomes. So that's not too hard. Previously, we have not laid out ARA methods for obtaining pi sub D of A, but we will shortly. Some of the options that we have are somebody who is seeking a Nash equilibrium, We can have an opponent whose analysis mirrors that of a decision maker, which is very close to a Bayes-Nash equilibrium. We have an opponent who might be a level K thinker, and we might have a non-strategic opponent. So those would all be different models for the thinking of our opponent, and each of these is going to impose a different cognitive burden upon the decision analyst who is trying to model the opponent. And so we are going to show how that cognitive load depends on the different situations that one has. The table I'm going to show you on the next slide displays the quantities that Daphne must assess in order to be able to do a level K analysis or other kinds of analysis. Row 0 is going to correspond to the utilities and beliefs of Daphne and Apollo, and these are the true utilities and true beliefs, and often these are not known. Each subsequent row is the additional utilities and probabilities that Daphne must assess in order to perform a level K analysis. So the first column contains what Daphne believes are the utility functions that Apollo ascribes to her. The second is the probabilities of the outcomes conditional on both her action and Apollo's. The third is her opinion of what Apollo thinks is her distribution for what he will do. The fourth contains the utility functions that she ascribes to Apollo. The fifth column contains the conditional probabilities of the outcome given her choice and Apollo's that she thinks Apollo holds, which is not the same as the one that she thinks herself. And finally, the sixth column contains what she thinks is Apollo's distribution over her own choice, her own actions. So that's the table that we have. And the first row is lowercase because those are not random quantities, even though we often don't know them. The subsequent rows are going to be random quantities because these are her subjective beliefs about these things. Now, if you're going to do traditional game theory, in which you assume common knowledge and everybody knows that the probabilities and utilities are all known, then you're going to use cells 01, 02, 04, 05, and you assume these are known. And obviously that is unrealistic because it's very unlikely that I will know exactly what Keeming thinks is going to be the probability of a successful bomb attack or something like that. If I have a non-strategic opponent, so I'm imagining that this guy is just basically tossing a coin and doing whatever the coin tells him to, then the non-strategic analysis requires cells 01, 02, and 03. And for the 03 cell is historical data. If we're talking about predicting a hurricane, we know how many times in the last 100 years a hurricane has struck New Orleans. We know what the distribution of the severity of the outcomes was. That's all stuff that comes from historical information or expert opinion or any of the usual mechanisms. Now, suppose we've got an adversary who is a Nash equilibrium seeking opponent. Then they're going to require cells 01, 02, 11, 12, 14, and 15, and it uses those last four cells to infer 03. And you recall that pi sub d of a, that's the hard one. And you have to use information from this row in order to estimate that. And in the next talk, we'll be more specific about how that is done. If you have a level K thinking opponent, well, a level 0 thinking opponent is non-strategic. So we know how to handle that one. But if you go to a higher level, you're going to need cells 01 and 02. And those are Daphne's utility and Daphne's risk assessment of the outcomes conditional on the choices. So those two are not hard. But you're also going to need, for the level 1 analysis, cells 14, 15, 16, which produces 03. And for a level 2 analysis, you use 11, 12, 13. That gives you 16. And then 16 with 14 and 15 will give you the 03. That's the hard one you need. And then if you want to go to beyond a level 2 thinker to a level 3 thinker or a level 4 thinker, it's the same pattern. You're just moving deeper down in that table from the previous slide. And the final solution concept that we want to consider is the mirror equilibrium one. And that's going to require cells 01, 02, and then a consistency condition that relates 14, 15, and 16, and 11, 12, and 13 to produce 03. And that consistency condition basically says that you and your opponent are both thinking about the problem in the same way. You're mirroring each other's analysis, but with uncertainty. And one main message that you get out of this right away is that there is no easy path here. All of this stuff is hard, and I will simply add, parenthetically, that if you do serious traditional game theory, that's hard too. There isn't any shortcut to finding a good answer in a strategic game. Now I would like to talk a little bit about a routing game. And here is a simple version in which you have a starting point, a terminus, you have a road network. Your opponent can plant IEDs at various vertices around that network. You do not know how many IEDs your opponent has, but in this simple case, we assume that we have a high probability that it's 1 or 2, not 7. So that's sort of the way we're thinking about this here. And we're going to let things, we're going to do a mirroring analysis in this problem. Now, the defender, Daphne, has imperfect information about the placement of the IEDs, and she doesn't know the attacker's resources and utilities. And symmetrically, the attacker, Apollo, has probabilistic knowledge about the route choice, the convoy value, and the defender utilities. But in this situation, a common knowledge assumption is clearly untenable. Daphne doesn't know what Apollo's utilities are. She doesn't know what resources he has. That's stuff that she can make guesses about, and as a Bayesian she will, but she doesn't have common knowledge. Similarly, Apollo doesn't know whether this is a valuable convoy or not, doesn't know how risk-averse Daphne may be. So all of these things are unknown. And here we're going to assume an additive structure which makes sense. The additive structure basically says that the damage the convoy receives adds up over time. So if it gets damaged at the first vertex and damaged at the second vertex, the total damage is the sum of the damage at both. And so that's the additive structure that's going on here. So Y is going to be the defender's privately known loss matrix, which is unknown to the attacker, but this is what Daphne really knows. She knows the value of her convoy, and she knows how bad getting damaged at vertex 1 is, how bad getting damaged at vertex 2 is, and so forth. X tilde is the random variable which the defender uses to model the attacker's gain matrix. And we're not assuming that the gain and the loss, that we're not assuming a zero-sum game, so the loss is not equal to the gain, but we do assume that a loss to Daphne is a gain to Apollo, maybe a large gain, maybe a small gain, but they do have opposite signs. So the gain matrix is what Daphne believes is Apollo's utility from an outcome. Y tilde is the random variable that Daphne uses to say what she thinks Apollo thinks is her loss function. So that's what Daphne thinks Apollo thinks is how much she regrets an IED at each vertex. A tilde is going to be the choice that tells where Apollo places the IEDs, and R tilde determines which route Daphne is going to take. And A tilde and R tilde are both going to be random variables because Daphne will not know these with certainty, and Apollo will not know her route choice with certainty. Now we're going to have an algorithm that's going to sort of set this up, and we'll see why it's called a mirroring argument in a minute. We're going to let X tilde have a distribution F, Y tilde have a distribution G, A and R are in the action sets. So the defender is going to start off with some pair of probability distributions that's not degenerate, but that's all you need. So you've got P naught and Q naught. P naught is the distribution over the attack space, and Q naught is the distribution over the route choice. And now we're going to iterate between these two things. We're going to find the solution for the initial Q naught. That gives us a distribution for the attacker's choice, which we're going to denote by P sub k plus 1. And similarly, we're going to have the defender's choice is going to be the random variable that represents the solution here. And so R tilde is going to have this distribution, A tilde is going to have that distribution. And it's called a mirroring argument because this coupled set of equations, one represents what Daphne is trying to do, the other represents what Apollo is trying to do, and they're trying to do it in the same way. So they've just got so Daphne has a model for how Apollo is trying to solve the problem, and they alternate. And as we will see momentarily, if you implement this algorithm until convergence, then you're going to find an equilibrium solution, and Daphne should then choose the right choice that maximizes, that minimizes her loss with respect to her true loss function y, not the y tilde that represents the random loss function that Apollo ascribes to her. And there are two results here. One is that a mirroring fixed point solution does exist for this problem. So under the assumptions we've made, there will be a solution. And secondly, if there is a total order on the action space A and D, then such that you have this increasing difference and decreasing difference relationship with respect to those two V and W, then this adversarial risk analysis algorithm will converge appropriately. And the second theorem is a little bit deep, but it is absolutely satisfied if the gains and losses are of opposite sign. Then it's a knockdown, no problem at all. We have examples in which it is satisfied if some, but not all, of the outcomes are of opposite sign. So there's a weaker statement that's still true here, but if you want to be guaranteed, then you're in a situation where Daphne's gain is Apollo's loss, Daphne's loss is Apollo's gain. If you've got that structure, then this is going to work. And in general, finding these fixed point solutions in game theory is a really hard problem. We'll talk more about that in the context of auctions in a little while. But for the special structure of this routing game, it turns out that we have a provably convergent algorithm that will do the job that we want. And the mirroring argument provides an explicit mechanism for figuring out how your opponent is going to think about the problem. If you believe that your opponent is trying to do a mirroring solution, then you use your subjective beliefs to put prior distributions over what you think are the opponent's loss function, what you think the opponent thinks is your loss function, and then the mirroring argument allows you to go through and produce what is your best guess, fully incorporating all of your uncertainty about the opponent's choice. And then you maximize your expected utility against that distribution. And one of the things you quickly see here is that basically in this type of game, whoever has better information is really advantaged. That's not a surprise. In any sort of adversarial situation, if your opponent knows more than you do, you're in trouble. And that should not be a surprise. In some sense, this whole thing can be traced back to the purloined letter, in which Inspector Dupin refers to a schoolboy who played the game of evens and odds, holding either 2 rocks or 1 rock behind his marbles, behind his back. And the boy was phenomenal. He was always successful. He won all the marbles in the school. And the schoolboy explains that if an arrant simpleton is his opponent, then the schoolboy the schoolboy reverses for the arrant simpleton, and for an opponent of slightly greater intelligence, he holds fast. And that means that he's outfoxed his opponent because he built a model for the decision making of his opponent and then maximizes expected utility against that. And in some sense, that's what we all do. If you were playing a game of chess with a 5-year-old child, you play one way. If you're playing with your postdoctoral student, you play a different way. You've built a model for how deeply your opponent is going to think, how good they are, and then you maximize your expected utility in terms of time and energy and so forth by the appropriate activity. So I would assert that in many situations, we informally do this type of modeling of our opponent and then proceed accordingly. Another game that I want to talk about is La Relance. And this is the Burrell game. It was invented by Emile Burrell about a decade before game theory got started. And it's been worked on by lots and lots of other people. Besides von Neumann and Morgenstern's Theory of Games and Economic Behavior, Chapter 9, it was also addressed by Richard Bellman and David Blackwell. Sam Carlin jumped in on it. Thomas Ferguson and his son Chris Ferguson are working more recently in that area. And of course, Emile Burrell himself, who actually solved this problem without an explicit understanding of minimaxity and modern game theory. So a whole lot of people have worked on this problem. It's really simple to describe, but it turns out to be really fiendishly difficult to solve in a general way. So we imagine that Lisa and Bart are playing the game La Relance, and they each ante $1 into the pot. Then they each independently and privately draw a number from the uniform 0-1 distribution. Bart looks at his number and decides whether he's going to bet B dollars or fold. If he folds, he loses his ante, and Lisa gets his dollar. If Bart decides to bet, then Lisa knows that he's bet and now decides whether or not she is going to match his bet with a bet of B dollars, or whether she will fold and forfeit her ante. If they both wind up betting B dollars, they compare their two numbers, and whoever has the larger random number wins the pot. So here are the outcomes from Bart's perspective. Bart can lose $1 if he folds. He'll gain $1 if he bets and Lisa folds. He'll gain 1 plus B dollars if he bets, she bets, and his X is greater than her Y, and otherwise he loses 1 plus B dollars. So the expected value of the game to Bart is going to be this thing. And we want to find the strategy that Bart should use in order to maximize his expected return. Bart needs to have some kind of bluffing function, g of x. And g of x says, what is the probability that Bart will bet given that he has observed that he drew x? And if he can find the bluffing function that maximizes the expected value of the game to him, then that's what he wants to do. And if we write the whole thing in terms of this bluffing function, the expected value of the game to Bart is the quantity that we have up there. And clearly the critical question is, what is the probability that Lisa bets given that Bart bets? Or the probability, 1 minus that is the probability that she folds given that Bart bets. So we need to know how Lisa is going to process Bart's information. Well, Bart is going to have to mirror the thinking that Lisa will perform in deciding whether or not to bet. Bart knows that Lisa's opinion about his X is going to be updated by the fact that he decided to bet. The fact that Bart bet B dollars is a signal that maybe his X is pretty large, or he could be bluffing. And so Bart has a subjective belief about what Lisa thinks is his bluffing function. We're going to call that G tilde of X. So Bart thinks that Lisa thinks that his bluffing function is G tilde of X. And there are many reasonable things that could happen that would give that result. For example, Bart may have set things up so that Lisa observed him reading Chapter 9 of the Theory of Games and Economics Behavior, in which case it would be natural for Lisa to assume that he's going to play the minimax rule. It could be that Milhouse has told Lisa that Bart bets with probability X when he holds X. That's not a crazy rule. Or it could be that somehow Bart has given the impression that, if he's got a number bigger than 0.5, he goes all in. If he's got a number less than 0.5, he always folds. All of those would be reasonable things, and Bart might use some process of disinformation to convey this impression to Lisa. However it happens, Bart has some belief about what Lisa thinks is his bluffing function, and we call what he thinks, she thinks, he thinks is G tilde. And so given that Bart bets, Bayes' rule says that Lisa's posterior distribution over the density of his X, the number that he drew, is going to be G tilde of X over the integral of G tilde of X. In the context of narrative forecasting, let me simply say that it turns out that if G tilde is a step function, then the posterior distribution reallocates all the weight below x naught to to the right. So Lisa, if we have got G tilde being a step function, then Lisa's posterior is simply going to upweight everything to the right of x naught. So in this analysis, Bart believes that Lisa calculates her expected probability of winning as the probability that Bart's x is less than her known y, given that Bart decides to bet, and y, capital Y, is unknown to Bart. So from Lisa's standpoint, the expected value of the game to her is going to be 1 plus b times capital F tilde, the integral of the density that we had on the last slide, minus the probability that she loses. So if she goes in, then she either wins or she loses. The probability that she wins is going to be F tilde of y. The probability that she loses is going to be 1 minus F tilde of y. And she knows that she loses her dollar if she folds. So whenever that thing is bigger than the dollar that she would lose from folding, then certainly Lisa should bet. And if we do the algebra on this, it's going to turn out that Lisa will bet if and only if F tilde of y is greater than b over 2 times 1 plus b. I'm going to let y tilde be the infimum of the set of y such that that condition holds. And it turns out that the probability that Lisa has drawn y bigger than y tilde is going to be 1 minus that. And so the expected value of the game for Bart, given his thing, given his x, is this quantity, where we're using the y tilde that we derived up there. And so far this is all notional because we haven't really figured out what G tilde is. But if we had a G tilde, then we can plug in and start going. You can rewrite the previous equation so that the expected value of the game to Bart is -1 plus c times g of x, where c is that thing. Now, when c is positive, Bart should clearly bet. And when c is negative, Bart should clearly fold. It's a very simple thing. If he thinks he's going to win money, he'll go all in. If he thinks he's going to lose, he's going to back out. And that all depends upon whether c is positive or negative. So that tells us, in fact, that this g of x that Bart uses should be a step function. It's not a bluffing function. He's not going to bet with certain probability if he holds. He's not going to bet with probability 1/3 if he holds x equals 1/3. Instead, this says if he thinks that the odds are in his favor, then he goes all in. If he thinks that he's going to have a loss, he backs out, backs away. So we now know the form of Bart's solution. His bluffing function should be a step function, and the only question is, where does it take a step? Well, in this case, one can solve it, and if x is less than Lisa's y tilde, then Bart bets if y tilde is greater than b over b plus 2. He folds if y is less than y tilde is less than b over b plus 2, and otherwise he can do whatever he likes. You can do a sanity check on all of this to see that you get the right answers when you plug in, a bet of $0 and things like that, where it would not be a problem. So in this situation, the expected value of the game to Bart is going to be the integral over all x's, the integral of the values of the game from all x. And of course, you remember that Bart is disadvantaged by the order of play here. He's the first mover, and Lisa gets to observe what he does and then make her decision. So in classical game theory, Bart is always going to lose money. And if Lisa is smart enough to play minimax, that's exactly what happens. If Lisa is playing the minimax rule, then there's really no room for Bart to maneuver here. He is going to be a money pump, and all the classic results go through, and basically the expected value for the game to Bart is he's going to lose b over b plus 2 squared dollars on average each play. That's the way it should set up. There is a small difference from the classical game theory, because in the classical game theory, Bart is supposed to bluff. If he does not bluff, then Lisa's optimal solution shifts, and she can win even more money from him, because the bluff keeps Lisa honest by forcing her to play with a pretty good y. And if Bart doesn't bluff, then she can go to a lower y and win more money from Bart. But here, we're playing one game, and he's not trying to pin her down. The rules are all set. He's figured out what she's going to do, and if it's minimax, there's no advantage to him. But in the real world, people behave a little differently. Poker players are rash. Poker players are overly conservative. If Bart believes that Lisa is rash, that means that she is betting when she holds a y tilde that's less than the minimax b over b plus 2 that she should use. And in that situation, it turns out that Bart should bet whenever he holds an x that's larger than b times 1 plus y tilde over 2 times 1 plus b. And in this situation, the value of the game to Bart is going to be this thing. And sometimes that's strictly positive. And always it will be larger than the minimax money pump that Bart is when Lisa is playing, when her rule is exactly to bet when y is greater than b over b plus 2. So if Lisa is being a little daring, Bart can exploit that. And if she's too daring, he can actually make money as opposed to losing money more slowly. Even better is when Lisa is too conservative. In this case, the rule is that Bart should always bet and make his money off of Lisa folding. Because when Lisa is too conservative, then she is going to not bet when she should, and she's going to fold, and that puts $1 in Bart's pocket each time. There are a couple of nice things about this. One is that the analysis of the Burrell game extends immediately to situations that are hard. For example, if you don't have a uniform 0-1 distribution, they're drawing from something else, then essentially there is no known solution to that variation of the game. There's two Japanese authors who claim that they have solved it for independent draws from the Fairley-Gumbel-Morgenstern distribution, and maybe so, but that's not really a very big generalization. In contrast, in this framework, the probability integral transformation immediately gives us what the rule should be for draws from any other distribution that you care about, and more interestingly, for dependent distributions. Because really what everybody wants to do is figure out what happens if you're dealing a deck of cards. And if you're dealing a deck of cards, if Bart holds the ace of spades, he knows that Lisa does not hold the ace of spades. So there's an enormous amount of information from the dependency structure in that. And with a straightforward analysis, one can get both of those results in this situation. And I say the analysis is trivial in Hardy's sense. There's a famous story about Hardy giving a lecture, and he said something was trivial, and the student said, "Are you sure it's trivial?" And Hardy walks out and comes back 2 hours later and says, "Yes, it is trivial." But that was because his definition was that if the first approach that represents itself to a mathematical mind can be carried forward without obstacle, then it's trivial. And that doesn't mean it's fast. It just means that it's direct. Another thing, well, there's another nice thing about this. You can extend this to the case of 3 players. So if Bart, Lisa, and Milhouse are playing, Bart can have opinions about what Lisa thinks, Bart can have opinions about what Milhouse thinks, Bart can have opinions about what Milhouse thinks Lisa thinks, and Bart can have opinions about what Lisa thinks Milhouse thinks. And this gets us away from the classic game theory in which everybody has to have the same opinions about each other and know what those opinions are. It's entirely possible for Bart to think that Lisa is rash, but he also thinks that Milhouse thinks Lisa is conservative. That's a perfectly reasonable thing to happen around a poker game, but it's not expressible in the traditional game theory where everybody has common knowledge and agrees on what the distributions are. Another issue that might arise in this type of game is the assumption that Bart knows exactly what Lisa's bluffing function is, that g tilde of x. And what seems more realistic is that Bart thinks there might be 1/3 of a chance that Lisa thinks he goes all in when he holds a number bigger than 0.5. He also thinks there's 1/3 of a chance that she thinks that he bets with probability x when he holds x. And there's also a probability of 1/3 that she thinks that he's playing minimax. And so he can find the solution for each of those 3, get a mixture distribution that represents her choices, and now he's going to maximize his expected utility against that mixture distribution that represents his full uncertainty about what solution concept Lisa thinks he is using. And so that's not it's not simple, but we know how to do that. If we let g tilde be a power function, so g of x is equal to x to the p, that's not a crazy type of rule. On the left panel, for a bet of $2, this is the minimum value at which Bart should play. And you can see that as p increases, he requires a larger x value in order to bet. And over here on the right panel, we show the value of the game to Bart as a function of p. And he starts off being a money pump, but up here, he crosses 0. And so at that point, Bart is making money in the game in expectation as opposed to losing money in expectation. So in this framework, it is actually possible under certain circumstances for Bart not to be losing all the time. One last thing I'd like to show in the last 5 minutes is how you handle continuous bets. This turns out to be a really hard problem. Sam Carlin, who was just a bear for calculation, worked really, really hard and figured out how to handle the thing when you could have bets of different sizes. So you could bet $2, $5, $10. He also figured out how you could play this game for 2 players, 3 players, 4 players. But the math, of course, just got really, really tricky and cumbersome and not pretty at all. But that was the closest they could come on handling continuous bets. Now we're allowing the possibility for Bart to make a continuous bet. And he can bet any amount of money between epsilon, where epsilon is strictly greater than 0, and some maximum amount k that represents all the money he has in his bank account. We're going to let g of tilde be the probability that Bart decides to bet after learning what he holds. H of b given x is the density on the amount that he will bet conditional on what he holds. So if he holds x equals 1/2, then what is the probability distribution over the amount that he actually does bet? And finally, b sub x is the random variable that's drawn from that density that tells us how much Bart bets. There's not a lot new here. It's basically the same framework we have as before, except now we've generalized it to allow a continuous bet as opposed to a fixed amount b of bets. This is going to, the expected value, the value of the game to Bart is this thing. And as before, he needs to find the probability that Lisa loses, given that he bet a specific amount of money, and we have to condition on all that. There are several dull slides that explain how to do this, and I'm going to skip those and get to our theorem. The theorem here says that if Lisa's posterior belief about Bart is positive and continuous, and b is in that interval, then the bet that Bart makes should be b star, the argmax of that thing, and delta star of x is going to be a value that maximizes that second expression. And if we allow those two quantities, then Bart's first order adversarial risk analysis solution is he's either going to bet or not bet. He's got a step function on whether or not to bet. If he's got a small value, he's going to fold. If he's got a larger value, he will bet. And then the amount that he bets is going to be non-random. There will be some amount. If I tell you x, then you will know exactly how much Bart should bet. And again, that seems reasonable given what we have seen before. And as an example, suppose that Lisa has a step function posterior on Bart. That's the simplest case, and so we're just working it out for, for the case in which Lisa's posterior on Bart's bluffing function is the step function that is reasonable for him to have. It turns out that when he holds a very small value of x, Bart will fold. When he holds a larger value of x, up to 1/2 plus epsilon over 2 times 1 plus k, then he's going to bet the minimum amount possible. Between that and that, he's going to increase linearly. And that's a result of the step function posterior that Lisa holds. If Lisa had a more complicated posterior distribution, which is certainly possible, then this thing would curve around in some way that was appropriately expressed Lisa's posterior. And then when he holds a really large value of x, Bart does what you would sort of think somebody would do. They would go all in and bet all the money that they have. So this is a reasonable kind of outcome for the situation that we have in the Laurelance game. Now, adversarial risk analysis allows us to very flexibly model the thought process of an opponent. If we think of our opponent as an idiot, we can proceed one way. If we think our opponent is really smart, we proceed another way. If we think that our opponent has a particular utility function that is different from what we might have, we can tailor the analysis to that. So from that perspective, this all fits pretty neatly into the traditional behavioral economics school, which shows that people have certain habits of mind, certain patterns of mistakes in doing their analysis, and if you know what those patterns are, you should exploit them. I mentioned before that we partition the total uncertainty into 3 components, each of which can be handled separately: the aleatory uncertainty, the epistemic uncertainty, and the concept uncertainty. And we will talk much more about this in the next talk about auctions, where these things are all nicely illustrated. We talked about convoy routing and Laurelance, and one gets interestingly different results than one finds from standard analysis using classical game theory. And finally, the ARA formulation leads to new research questions. And in particular, I'll point to the Laurelance game with more than 2 players, because now we can, I think, reasonably model Bart's belief about Lisa's thinking about Milhouse and Bart's belief about what Milhouse thinks about Lisa in ways that open up a new problem space. So that's the quick and dirty overview of adversarial risk analysis.